Okay, welcome back, everyone. This is the Virtual Residency Workshop 2023. It's Thursday, June 29th. This is our first session of the day. It's Research Networking Overview, and our speaker is Wallace Chase. So take it away, Wallace.
All right. Hello and good morning, everybody. Let me go ahead and I'm going to share my screen here. How's that coming through, Henry?
Looks great.
Perfect. All right. Let me go back here to, sorry about that. There we go. Let's share the first screen instead of the third one. All right. Good morning, everybody. My name is Wallace Chase, and today I'm going to be talking to you guys about how the internet is fine. I'm on Facebook right now. So we're going to have a bit of a discussion today about how networking in support of data-intensive research in particular is just not the same as networking for a general purpose use within any environment that we deal with. Okay, so is this going to make me into a network engineer? No, it's probably not going to make you into a network engineer. However, it is going to let you help navigate the world of the network engineer, dealing with research data and dealing with things in our world here. It might even help understand network engineers a little bit, but as a previous network engineer, I could tell you that sometimes we're just not all that understandable. So why exactly do we need to know this? Why, as facilitators, do you guys need to know what's going on in networking? Why does it matter? Well, that's because networking for a lot of folks looks a bit like this. It's a tangled mess. It's a lot of things going on. We don't know how it works, don't know what happens behind the scenes. And when you start to get an explanation from a hardcore network engineer, it often starts to devolve into this very quickly. So why should you be listening to me at all? So my name's Wallace Chase. As I said earlier, I'm the head of department for the Information Technology Services division here at the University of Otago in New Zealand. I have been around in the space for a little while now, and the cluster of logos down in the right-hand corner there are all the previous institutions I've been at and have been involved in the virtual residency now for many years. For Henry is very good at getting me to come back and talk to folks, and I do enjoy that every year. All right, so what is the difference in different types of data? Let's talk about that first. What is the difference between research data and kind of normal data out on the internet? That'll help us to define what the problem is and how we go about solving it. So normal everyday data out on the internet consists of web pages, consists of a lot of apps, consists of a lot of different things. This is what we would consider kind of normal internet traffic. This is what most people, that 99%, when they're on the internet, go out there to find, consume, publish, whatever. It's this type of data. Okay. Research data is a little bit different. It can be very large. It can be very unwieldy to move around. And requires specialty equipment. No different than moving a giant transformer requires special equipment to move it across the roads. It requires special equipment to move very large research data sets around, and special skill sets as well. Research data can also have some other funny characteristics that are not necessarily the same in normal internet data, what I'll say. And one of those is that it can be very much kind of continuous flows of large amounts of information, and it can just take up a lot of space on a network. So one of the things to look at, and one of the reasons why I chose this picture is a real good one, and I will ask for some feedback during this occasionally, so everybody get your little thumbs up icons ready. How many folks in here have used Amtrak to travel in the US, especially across the Western US? I have. I enjoyed it quite a bit. How many of you have been on trains that have been delayed on Amtrak, especially going across the US Midwest? Okay, lots there. All right. So one of the reasons for that, of course, is that Amtrak traffic is not prioritized on the railroads. The railroads are mostly owned by companies like the NSF and stuff like that, who move large amounts of freight around on those. So when you have traffic that's not prioritized, on there. It gets slowed down, it gets stopped, it gets delayed, those sorts of things. The same sort of things happen with research data. All right, so who's providing this transport across the internet or between institutions when it comes to research data or just internet data in general? So we have, first up, we have things called commodity or commercial networks. So those are companies like your AT&T, your Verizons, your Spark or Vodafone, if you're international. Those are the types of companies that you're talking about there that provide that service. You may have that service in your house today. So let's talk about the differences right now between commodity networking and kind of the research and education networking. And I like to use this chart because it kind of really emphasizes what the difference is between the two. So for a commodity network, if you put in about, if you have 100% of the effort there and you put in about 20% of it and you get 80% result, that's good. That's good business right there. You're putting in not a ton of effort and you're getting a good result that services the 80% of the people. On the research side, we usually have to do is put in 80% of the effort to solve the 20% corner cases of networking or data transfer. Not necessarily a great business model. Another way to look at this is I like to use this chart as well. So this is a chart of consumer complaints for the Consumer Financial Protection Bureau here in the US. So this kind of shows what so if you look across the bottom, it's kind of small text, but you can see those are different categories of complaints. Basically, this many people, 30,000 people complained about this particular thing. So if you are a institution like the CFPB and you are financially constrained in what you can do and staffing constrained, are you going to start on the right-hand side and deal with those complaints, or are you going to start on the left-hand side and deal with those complaints? So one of the reasons that they do this type of data collection is so they can look at it and try to solve those problems, solve that 90%, 80 to 90% over on the left-hand side of the screen there. Deal with those and you'll have dealt with the most of the problems. And the long tail is not as big of an issue. You deal with as much of that as you can. So this pretty well illustrates what commercial networks are dealing with. Research data is not the main driver for any large company out there on the service provider space. So if you're dealing with an AT&T or Verizon or something like that, research data is going to be in this long tail. It's going to be way down there at the end. It's going to be more difficult to deal with, but it's going to be servicing a smaller group of people. So they're going to deal with making sure that Facebook works well, making sure that all those types of things work well. Another thing to understand when you're talking about networks and commercial networks in particular is that they very heavily use what's called content delivery networks. So a CDN is simply a server that will sit within the environment of an ISP, an internet service provider, like an AT&T, Verizon, any of those types of companies, and it'll service up the content that is most generally accessed on the internet. So a lot of people, when you think about you're going on to, let's say, onto Facebook, or you're going on to Twitter or something like that, where do you think you're actually accessing that data from? Is it some mystery bank of servers somewhere in Sunnyvale in California? It's probably actually a server that's fairly close to you that gets the content that most of us access delivered to it. And so if you see on the right-hand side here, the companies are able to actually push that content down to the CDN where it's closer to the end user so that your traffic doesn't have to transit as far. So if you're in New Zealand, for instance, you would not necessarily go all the way to the main Facebook servers, wherever they may lie. You would instead go to what's called a content delivery network that sits often within the ISP that's providing you. Now, this is an interesting snapshot here, actually from the University of Otago, from one of our campuses, showing some of the traffic flows here. And we can see there on the left-hand side, the total amount of traffic in a particular time period of 2.52 petabytes. And then the other categories here are kind of interesting. So international commodity, this is the amount of traffic that we send that we either bring in or send external to New Zealand. So 462 terabytes of that 2.52 petabytes is considered international commodity. So commodity traffic is your Facebooks, your Googles, all those types of things, anything that's not necessarily going to another university or to a research lab. Domestic commodity, notice how that's much higher. So you have 734 terabytes of domestic commodity opposed to 462 terabytes of international commodity. Now, New Zealand's a fairly small country, about 5.2 million people. Most of the people on the internet within New Zealand are accessing the exact same things that people are accessing in the US or in Europe or in any other part of the world. And most of those things, those companies do not exist in New Zealand. So Google doesn't have a huge presence in New Zealand, these types of things. Most of the content that we're accessing is external to New Zealand. So this is a great example of that. How much of that is actually coming from domestic commodity, which represents a lot of those content delivery nodes, those CDNs. And then you've got international NREN. This is how much in that particular time period we went to another university or somebody on the research network, and the domestic NREN is basically between campuses or between areas there. So it's kind of interesting, that international and domestic commodity. Okay, now why is all this important and why does this matter? So the motivations behind commercial networks are pretty simple. Is to make large amounts of money in return for their shareholders. It's not necessarily to service those very, very specific niche areas unless there's a whole lot of money to be made in it. And as we all know, we're not exactly swimming in money out in the research space. So there's not a whole lot of money necessarily to be made there in the grand context of what AT&T or Verizon brings in a year. So they're not going to concentrate on what we're looking for here. They're not going to concentrate on supporting research data unless there's a whole lot of money to be made there. Because of that, over many years, the research networking community has sprung up, which has been community-led or state-led or regional-led. It's kind of depends on the area. Different networks that operate kind of like a Verizon or an AT&T, like one of those big commercial networks, but instead they're specifically tailored just for the needs of the research networking community. So they are serving universities, K through 20 schools often, libraries, research institutes, those types of things. They often have very specific rules around who and who cannot connect to the network. I know when I worked in South Carolina, there were some very specific rules around who could connect to the C-Light network there that were mandated by the state of South Carolina in order to preserve competition between carriers and that. But those big research institutions like the universities, like the polytechnics and community colleges and that were able to connect in and to get that different level of service. So at the end of the day, both the sloth and the giraffe eat leaves. They kind of have the same goal in mind when it comes to how to survive and what they like to eat. But they just do it in very different ways. And that's the same for commodity networks and research networks. They do the same thing at the end of the day, but they do it in very different ways because they're different animals. And if you combine the two together, you combine a sloth and a giraffe, you get a thing that's not necessarily anything that you would expect. So we typically don't do that. Okay, so now for a little bit more of a technical discussion here on exactly what's going on. I'm not going to go very deep into this. This isn't a technical talk. If you're a network engineer, you already know this stuff. If you want to know more about it, go talk to your local network engineer and they will be glad to tell you everything you want to know there. So let's talk real quick about how the internet came to be, because that explains a little bit of why it's hard sometimes for very large research data loads to go through. So back in the very beginning, when you had ARPANET, this is one of the diagrams from 1977 of the original ARPANET network there with PDPs scattered around the country in different areas. So the original goal of the internet, of networks, was for survivability when it came to a military situation, so a nuclear attack or something like that. This is important to remember because this is kind of the bones of how the internet was created and what the rationale was and what the original designs for it were. So you can think about it in this way: if you've got if you've got a network here, which I'm representing by the content, which is a steak and a raptor over on the right hand side, obviously there's an easy path right there, straight from one end to the other. But if you have something that comes in the middle, breaks that connection, you need alternate paths. So that you can still get to that tasty steak. That kind of gave rise to how the internet was originally designed. It's autonomous systems interconnecting using standardized protocols. So networks connect to networks, and they're all autonomously operating, but they're using standardized protocols to send information back and forth and to get what's called routing information. This is a visualization of what the internet looked like back in 2015. I'm not even sure you could visualize what the internet looks like today, given how big and interconnected it is. But this is kind of shows the level of complexity that's out there when it comes to how things interconnect on the internet. And this is all done with using different mathematical algorithms and that to predict how to dictate how traffic will flow and what paths are taken and that sort of thing. All quite complex. And not going to go into it here, but this is one of the very interesting things amongst many things about networking is that it is it becomes at a certain point of scale, it becomes a little bit magic how it all works. Okay, but let's talk real quick about some of the specifics here. So there are really three major factors that affect TCP performance. And transmission control protocol is kind of the most common way on the internet that traffic flows back and forth. So those are latency, buffer window size, and packet loss. And all three of those are very interrelated when it comes to talking about how data is transferred on the internet. So you've got a client and a server, and they're doing a series of communications back and forth with sending SYN packets, SYN-ACKs, and ACKs before they can send the data. There's kind of a dance that happens between the client and the server to figure out how to send the data, when to send the data, and to make sure that the data has actually been received on the other end successfully. So that's a big portion of how TCP works, as opposed to UDP, which just kind of blasts data out onto the network, doesn't care if it actually gets there or not. It just sends it and sends it and sends it and sends it. So UDP is not very commonly used for moving files that you care about. UDP is more used for things like what we're doing here today, for a Zoom transmission or something like that. If a UDP packet, if a piece of video or a piece of audio from my talk here doesn't get to the other side, we don't actually want to resend that data. We don't want to send it again later, because then it comes out of sequence and it doesn't really make any sense. So if you lose a couple milliseconds of my speech, you don't want to resend that in a couple more milliseconds just because it didn't get to the other side. It's useless information at that time. So TCP is typically used whenever you have any type of data that you care about, and you want to make sure that it gets from point A to point B in the same way. So think of a genomics data set or something like that. You don't want to lose part of that in transit. You don't want to lose a couple of sequences in there in transit. You want to make sure that everything gets from point A to point B. Okay, so packet loss. Packet loss is a real big issue when it comes to this type of traffic. So that's anytime we lose a packet, that then has to be retransmitted back over again. So every time you retransmit a packet, you are putting delay into the whole system. Oops, sorry about that. So anytime you input delay into the system, you end up with more packet loss. Latency is another one. So latency is a very large issue when it comes to moving large data sets as well. And that's the whole time, that round trip time from point A to point B. How long does it take you to get from one side to the other? Remember that this dance is going on between the client and the server. They're trying to figure out how fast to send the information. They're trying to figure out how make sure that everything's gotten from one side to the other. Okay, when you get packet loss or high levels of latency in there, you can have problems that manifest themselves very quickly. So this is a series of tests that was done by ESNet now many years ago, but that kind of shows what happens for throughput when you have increasing latency on a link with just a little tiny bit of packet loss. So you can see up there that on the purple link there, that's with no loss at all. And you're transferring a large amount of data. You get pretty good throughput. It does drop off a little bit just naturally due to the fact that it does take time to move stuff around no matter what you do. But you can see here on the other ones, when you inject just a 0.004% of packet loss into this data transfer, how quickly the throughput falls off. So you see those blue and red lines there, how fast the throughput falls off as soon as you get more distance, basically more latency. So the more latency you have, the more the throughput falls off if you've got any packet loss at all, even if it's very tiny amounts of packet loss. And the reason for this is fairly complex in some ways, but it can be summarized down into basically that dance that the protocols have to do to figure out if things have gotten there and to fix errors or fix packet loss. Means that the entire TCP protocol backs off on its sending rate as soon as it starts to encounter problems. When it backs off on its sending rate, it basically slows everything down, thinking that there's a problem with the link, and that may be due to congestion, it may be due to who knows what's happening. So it slows everything down and kind of restarts its whole process of ramping back up to figure out where that top speed is that it can handle. And so very small amounts of packet loss on the network impact this. Now you may say, well, why don't we just fix packet loss and that's good. That is good. We can fix packet loss. However, in most commercial networks, there's always a certain amount of packet loss, and there's always latency. So that comes back again to these all being autonomous networks interconnecting together. There's always the chance for errors. There's always a chance for faulty equipment or just equipment that's overloaded, that's not able to keep up with buffering of that sort of thing. And that amount of packet loss, for the most part, doesn't impact somebody who's just getting small amounts of data. If you're just getting small amounts of data, if you're just looking at Facebook, browsing the internet, even downloading a couple gigabytes worth of data, that's not going to impact you a ton. However, when you start to try to move terabytes or petabytes or multiple gigs, hundreds of gigs of data around, this impacts very quickly, and your speed falls off to almost unusable amounts very quickly. So this means a couple of things. Let's talk about the differences real quick between a WAN, a LAN, and a MAN. So a LAN, this is called a local area network. This is what a lot of you guys think of when you think of the network in your university or in your research institute. So it's often shorter distances are involved. It can be called an internal network. I put that in quotes there, though. It's switching and routing on the networking side of things, and it's often provided by you or your institute. So this is that wiring closet that sits somewhere on the floor of the building. If you're wired into the network, your cables all go back to a switch there, or your laptop or computer connects into a wireless access point, which is connected in the switch there. This is that local network within the building. Now, onto the local network within a building, you can get away with a lot of things. You can get away with moving large amounts of files and there be some packet loss or errors or that sort of thing because you're not going that far. You don't have much latency introduced into the system there. So a local area network can also be a little bit bigger than that. You can have multiple buildings to that connected all together within an area, but typically the distances again are fairly small in this case. So if you're on a campus and you've got a cluster of buildings that are all together, that would be still considered a LAN, even though you're going outside of the building or maybe outside of a layer 2 switching domain. Now, a MAN, a metropolitan area network, our connections are held together often by WAN links, which we'll talk about in a second, but these are larger geographic areas. So in this example, if you've got a campus, an east campus and a west campus, and there's a little bit of distance between them, this would be considered a metropolitan area network. Now, here's where you start to get into some issues when it comes to network design, and you really have to start thinking about large data transfers. because you've got more latency involved, you got more distance involved, you got more equipment involved, there's more places that things can go wrong. There's also more points where congestion can occur. So there's more points where traffic comes together, and you start to have to prioritize traffic if you don't have large enough links. University campuses are often metropolitan area networks, even though we don't always call them that, but they're often metropolitan area networks because they're large and spread out. Now, a WAN is simply just a link between two places that are fairly distant from each other. Oftentimes, WAN links will be provided by third-party providers. Not always, but often. So often you'll go to like an AT&T or Verizon or a CenturyLink or something like that and get either dark fiber or fiber optics that can connect you from point A to point B. Those typically on someone else's network. Although again, not always. Some people run their own fiber long amounts of distances. This is also where you start to connect into things like the internet and things external to your university. So why do we go over LAN, WAN, and MAN? Just simply because this is where you start to have as you get bigger, as you get more distance, as you get more congestion points, network engineers have to start thinking a lot more about how to deal with research traffic. And this is one of the things you'll commonly see if you're a facilitator is a researcher will have a network, will have a lab. They might have gone out and bought their own, 10 gigabit capable switch or 100 gigabits capable switch, put it in their lab, and they're moving data, large amounts of data around internal to their lab with very little problems. But then as soon as they start to actually collaborate externally to there, move it across the network, move it between institutions, move it around, things can get bad very quickly as far as the actual amount of throughput. So network engineers need to think about those things and design university networks or research networks at research institutions very differently from what you would design if you were just setting up a normal office network. So yeah, so it all kind of looks like this still, and hopefully you guys have some ability here to find Waldo in all of this mess. So again, this is really the reason for all of this. As soon as you start to expand out into that metro area, again, if you look up there, you see the local LAN, the metro area, and the regional, which can be considered the WAN. You can see how fast things fall out. So if you just have simply a big campus that's even just a little bit spread out, you can have these exact same problems just moving stuff between a lab where maybe a genomic sequencer is sitting and a data center where your supercomputing facility is sitting. So what happens when research traffic hits normal everyday networks? And if anybody's been on the internet for a while, you may go to this website, the 11-foot 8-inch bridge, and you know exactly what happens when research network hits normal networks. So things don't fit, things get jammed up, and everything slows to a crawl there. I like that second one in particular because you see the car behind it having to slow to a stop as well, due to the fact that the research network just jammed up the whole pipe. So this has adverse consequences. So performance issues for the researcher are obvious there, but performance issues for everyone else as well. So if you've got a researcher that's transferring a large amount of data, your network's not necessarily set up for it, the network's still going to try to move that data around. It's still going to try to get it done, but it will often cause performance issues for everyone else then also connected to that network. So the researcher gets frustrated, everyone else gets frustrated, and the IT staff gets frustrated. And what you end up with is hard drives or flash drives being put into the mail and sent around, which nobody necessarily wants. This is a very inefficient way to do it unless you're moving absolutely Herculean amounts of data, in which case it's actually a fairly efficient way to do it. Actually, a study was done on the effect of the post, basically the overall throughput on the post for data transfers as opposed to some of the technologies of the day, which was pretty interesting a couple of years ago. Okay, so but being able to collaborate is obviously, I wouldn't even say it's the future of science, I would say it is science today, and you need to be able to move around and share information and those sorts of things. So there are things, specialty networks and specialty designs that have come out over the years to support exactly this. And one is the Science DMZ. And a lot of you, if you've been around doing this for a while, you've heard of the Science DMZ. The Science DMZ, although it looks fairly complex when you look at a diagram like this, it's actually very simple. It's simply a traffic bypass for those high amounts of data, all that research data. It's basically a way to bypass the normal everyday network for those researchers and be able to put their traffic from point A to point B very easily over a clean route that doesn't have a lot of extra things in it. So one of the things that is common on all networks today and is getting more and more intense as time goes by, anyone who's in central IT like I am knows it's the bane of their existence is IT security. And I don't say the IT security team is the bane of my existence. I love them. They're wonderful. But actually having to deal with it and work on it, and that has become a very large part of what we do, simply because of the way the world is and the way people are in the world. There's money to be made by stealing data. IT security appliances like firewalls and that operate in a way that is where you have to remember these folks are selling their products. And if you're selling a product, no different than a commercial internet provider, you need to sell to the 90%, not to the 10% to make money. And oftentimes these products are very good. They may advertise, hey, got 10 gigs of throughput on this firewall. That's wonderful. But they're expecting that traffic that's going through that firewall to look like pretty normal traffic when it comes to what people do on networks and on the internet, which means they're looking for the same things those internet service providers are looking for, which is small amounts of data being accessed frequently, not necessarily very large chunky flows of data. So a lot of firewalls don't work very well for that, and that's why specialty security arrangements need to be made and specialty designs need to be made, especially around security when it comes to that, because those devices, those firewalls, those traffic inspection devices and that can really wreak havoc on a scientific data flow, because they're introducing latency into the question. So it takes time to process that data as it goes through there. Even if that time is tiny, it still takes time. And that can back up the whole system. A lot of firewalls are set up where you may have 10 gigs of throughput, but each individual flow can only be a maximum of 1, for instance. That was very, very common many years ago, where firewalls would only do a maximum of a 1 gig of throughput, even if they said they were a 10 gig firewall. And a lot of firewalls today in practice are doing the same thing. There's some that are able to handle the larger traffic flows, but those are often horrifically expensive and can be a little bit of an overkill. If you can just design, network engineers can get together and design a network where some of those big predictable traffic flows, for instance, if you have a sequencer sitting over at point A and a data center over at point B, you can design how that traffic is going to flow between those 2 points and know that is clean traffic. It's from a known source to a known destination, and design out a security policy and a way of routing that traffic. That means it doesn't have to go through all the normal checks that a student browsing the internet on their malware-infested laptop has to go to. All right, so there's a bunch of different pieces of the puzzle when it comes to putting together a solution for the network for a researcher by networking folks. One is a Science DMZ, of course. The other is a data transfer node, often called a DTN. So that's a very specialty server that will sit at that point A and that point B, that'll actually be able to move data at a certain data rate. So a lot of computers can't handle, even if you have a 1 gig card in your computer, often they can't actually handle 1 gig of a solid transfer of data in there. There's specialty things that need to be tweaked, software that needs to be set up, and DTNs are where you do that. So you have these specialty nodes that sit out there that allow you to transfer data from point A to point B, so that you can use some fairly sophisticated protocols like grid FTP and stuff like that to actually move that data. Globus is a very popular one that we see a lot of utilization of here in New Zealand. We have a pretty advanced Globus network set up between the supercomputing center and the different universities and research labs that use that, they're all using Globus to move stuff back and forth, and that works pretty well. I'd encourage you to check that out so you can get a free client that you can just log into and look at and see how it works on Globus. So specialty storage, network engineers who are dealing with research talk to the storage admins a whole lot. So mapping out in the network where different types of storage are, where large storage arrays are, what their capabilities are, how they connect in the network, do they have DTNs in front of them, those sorts of things is very important. So the network engineer and the storage engineers end up being very close to each other and working together in a research situation. And then you have all the other parts of the research and education network ecosystem, which are NRENs, so national research and education networks, regional optical networks, and just RNE networks are some of the different titles that you can be called for that. Okay, so again, a DTN, pretty simple there. It's just a high performance server or computer. It's got a lot of network connectivity that's been specially tuned to move large amounts of data. Has a dedicated connection often to the storage that it's servicing or to the instrument that it's servicing, and it's able to move that data back and forth. So a DTN could be just about anything, any type of software on that. It's just something that's been specially tuned to help move that data back and forth and to often utilize the science DMZ. All right, so different types of networks that are out there and kind of a look at the ecosystem. So one in the US is your state, your regional networks. So these are things like, if some examples on here, if you are in Michigan, Merit Networks would be your network of choice if you're a university, connecting you into the broader ecosystem there. So each area or state in the country has some sort of connectivity for all intents and purposes. That connects you into one of these specialty networks. You can see on there North Carolina with MCMC, Scenic in California. Some of these networks are very highly advanced and have a lot of connectivity. Some are a little bit smaller and just service the large research institutions in the area, but they all serve the same purpose, and they're all there to be kind of your campus's first point of connection into the world of research networking. Okay, so why am I about to talk about all this? Well, so relationships are very important in the networking world. So remember back to the beginning where I said the networks are just, the internet is kind of autonomous systems all working together. Relationships between these various institutions are very important when it comes to especially scientific data flows. Network engineers have to work very closely together to make sure that that things are actually working, to troubleshoot problems when they come up. And these are some of the, I would say, some of the main differentiators, almost more than the technology, when it comes to research networks, is the fact that these relationships exist. We're able to call up if we've got a problem moving something from point A to point B. The network folks that work in these optical networks and research networks know who to call, who's the next connector in the piece of the puzzle to connect to and to troubleshoot that problem. Well, there's an example right there of Merit Network, and anybody who's from Merit Network or from any of these networks that I show diagrams for. Yeah, the diagrams may be a couple years old. You don't need to send me your most recent one. These are just examples. All right, so another type of network that's in these systems is called exchanges, or POPs, point of presence. And these often connect larger regional areas. So like a couple of states or an area of the country will connect that all together. We'll bring different local networks, bring state networks together into an area and provide greater connectivity in an area. So the Pacific Northwest Gigapop is a very good example of that, kind of consolidating all that traffic on the West Coast into one organization, one set of points that is able to connect to the broader community, connect to the global community even, and have that different connection there. And then we've got national networks. So in the US, there are several different national networks for different needs that kind of touch the research community. Internet 2, obviously the main one that most universities are connected to there But there's other where NOAA has one, and ESNet has a very highly advanced network for the national labs like LBL and stuff like that, that all connect together for moving data between their different supercomputing centers. So Internet 2 there, this is a little bit older diagram, but I think mostly still accurate, but this is kind of their points of presence and interconnections around the country. You can see they cover most everywhere in the country. ESNet has a similar looking network, but also has very much has connections that go outside of there, going to the various different laboratories and supercolliders and stuff like that that are in Europe. N-Wave, very much the same. And then you have in my country of New Zealand here, we have very similar situation. We have the RANS network that interconnects all the different main areas in the country where there are universities or research sites. So you have we have national networks in the US. National networks exist all over the world as well. So different countries have their own national networks. Most areas of the world are covered by one in one way or another, and they're kind of responsible for that interconnectivity. Now, when you have countries that are not necessarily quite as divided up as the US into different states, you may have just one institution that services the whole country. So RIANS in New Zealand, for instance, kind of operates as both that local network and as the national network. All the universities connect directly into it instead of having that middle state network. It just depends on the size and the complexity of the country and the politics around how things were set up when they were originally built out. Okay, so some examples of other networks, national networks around the world. You've got Canary here in Canada, and you've got RNet in Australia. So every country will have a very similar diagram. So, and then when it comes to actual international connectivity between different countries, I'm going to use kind of New Zealand here as an example. So it's all done via mostly subsea cable links across the world. And there's some really interesting websites out there if you're interested to go to, where you can go and you can look at all the different subsea cable links in the world and where they go and who owns them and how old they are and that sort of thing. It's a very, very interesting dynamic map, which is where I got this from. It's very interesting to go out there and take a look at that. This is one of our main links into New Zealand called the Haiviki cable system. This was put in about 6-7 years ago and was partially funded by RIANS and by the New Zealand government in order to increase research connectivity in New Zealand. So it's a very complex cable system that runs from Oregon to Hawaii, down to New Zealand, over to Australia as well. And these links happen all over the world. This is just an example from some material that RIANS had put together a couple of years ago, but the interconnectivities of the national research and education networks is immense. It's something that is being worked on constantly, making sure that it is up to date, that we have capabilities on new cable systems, that we have the amount of bandwidth between different points on the globe that is necessary. And there's a tremendous amount of work that goes into that. There's connectivity to just about every part of the planet when it comes to this system. There's even work going on right now to get better connectivity into McMurdo in Antarctica as well, which is kind of the final frontier for getting connectivity for data science. The research network community also provides other things as well. So these are community organizations run by the community for the community. So they provide services such as Eduroam, which is, most of you should probably know what that is, which is where you can connect up to wireless internet at other institutions using your home institution's credentials. You don't need to have a guest account. You can just kind of log on. And things like EduGain, which is that is that authentication backend. So you're able to authenticate using your home institution's credentials into other institutions' resources, such as scientific instruments and stuff like that. A bunch of other examples of products like that, but this is all produced by that international community there. So let's go through just real quick an example here of moving some data. Let's say that we are in an institution in the US we'll just pick Oklahoma University because we can pick on that fairly easily here, moving to my home institution of the University of Otago down on the South Island of New Zealand. And this will demonstrate kind of the importance of those relationships and how complex things can get and how difficult it can be to deal with stuff if you don't have those relationships and don't have this community supporting you. So starting out in Oklahoma University, you need the information technology group. So that's who you're probably connected to if you're a researcher or a scientist. They're the ones providing the networking for you. So any problems that happen there would need to be dealt with by them. After that, after it leaves University of Oklahoma's network, it would go on to OneNet, which is that state-run research network that connects across Oklahoma. After that, the Oklahoma connects into the Great Plains network, which is kind of that regional connector for all of the central United States there. They'll then offload the traffic over onto Internet 2, which will take it across the country on its network. It would then hit the Pacific Northwest GigPop because that's where we have the connectivity. And Scenic is involved in helping to run and operate that as well in California. And we'll go on to a exchange called the Pacific Wave Exchange, which then will transmit the information across the ocean, across that Haviki cable system that is, of course, operated in part by RIANS. Within New Zealand, then RIANS will take that traffic and hop it down the country to where the University of Otago is located. So in order to get the traffic from the University of Oklahoma's beautiful campus to our beautiful campus here in New Zealand, it takes all those different institutions working together, having a network that is tuned and designed specifically for moving research data around. Because remember, if you have even a tiny little bit of packet loss or any types of issues within there, it can have drastic effects on the actual overall throughput of the data from point A to point B. So it's very important to have that. And the nice thing is that at the University of Otago, if my researchers are having a problem getting data back and forth between University of Oklahoma, we know my IT staff, my network engineers know who to call. They can call up RIANS, who knows who to call the next part of the chain is, and all these institutions will gladly work together to solve the problem to make sure that research data is able to move from point A to point B. Now, why do I make such a big deal of this? So if you're connected to a commercial provider, so you're just paying a company to provide your internet access, it'll work very well for the 99% of your students and staff. They'll be able to go to Facebook and all these types of things, no problem whatsoever, even move decently large files around. But when it comes to moving large amounts of research data around, large data sets between supercomputing centers, between storage centers, genomics data sets, whatever you may have at your particular institution, there's often no one to call if something goes wrong, and things will go wrong when it comes to larger data sets. So your local provider, that is commercial provider that's providing that internet access, doesn't know necessarily end to end how that traffic's getting from one point on the globe to another. They don't know because they don't need to know. They simply sell the traffic to the next, often lowest bidder to move the traffic around. So their relationships are purely commercial. They say, I need 200 gigabits of connectivity to the internet. They'll buy 200 gigabits of connectivity to the internet. They won't necessarily even know how that connectivity is, who's providing that, who are the companies underneath the hood that's doing it. It's simply just a commercial arrangement to get the traffic from point A to point B. So your traffic may go in different ways through different providers and that, through different qualities of links, that sort of thing, with no real ability even for your commercial provider to help you out if there is a problem that's outside of their network's control. This is where the power of the research networking community comes in, where we can control, troubleshoot, and diagnose end-to-end and actually make sure that these things work, because it is very tricky to get these things to work. It's not something that the internet naturally does well. It's getting better at it, but it's still not there fully. So getting from point A to point B, not as easy as you would think. Okay, so a couple different things before I wrap up here. One is the requirements of the data intensive researcher and the service profile of a traditional computer network don't always align, especially commercial networks. So networks interconnect to networks, to networks, to networks, networks. You can have a lot of different networks involved when you're transferring data, even just within a smaller area, say a state or something like that. If you're on a commercial network, you can have a lot of different commercial networks involved that are moving the data around. And if you don't have that end-to-end visibility or that end-to-end ability to troubleshoot, things can get very difficult when it comes to large data flows. Networks are exponentially complex the more connections you have. So it's one of these things. Remember, this is a massive complex of interconnected autonomous systems. And it gets more complex the more connections you have. There's more options for how data flows. There's more algorithms involved. It gets very complex very fast. And NRENs are really at the core of that. So that we provide that connectivity and that community to support data intensive science. And research networks are there for your transfers. So if it's not working, ask for help. Don't know how many times over the years I've had conversations with researchers or something who will say, "Oh, I've been frustrated. I've been trying to move this data set for years." Well, we just send flash drives back and forth because we could never get it to work. Reach out, make sure that people know how to ask for help. Make sure you know in your institution as research facilitators who you can talk to within the networking side of things, who's kind of that person or that group that's responsible for taking care of research data flows. Ask for help. If you don't get anything within your institution, go to your state network, ask them for help. The network engineers who are passionate about this and who work on research networks live for this kind of stuff, live for figuring out large data flows and helping diagnose these problems. So you don't get to be a network engineer unless you like to solve tricky problems and diagnose things. That's pretty much the core of the job some days. And if your data must transit it, it's your network. So make sure that you take that ownership of it and talk to the folks involved and make sure that everyone's helping to troubleshoot what you're doing. At the end of the day, we're hoping to enable our researchers to be like the proverbial velociraptor riding a shark with a rocket launcher. That's all for me. Thank you, everybody. I've got a little bit of time, I think, right now to take some questions from folks. If anybody's got any questions, other than that, I will turn it back over to get on with the rest of your day.
So I know I have a question of my own, but I want to throw the floor open to others. So 5 brownie points to whoever asks the first question. Don't make me award those brownie points to myself.
Wallace, this is Tom Marseille from Washington and Lee University. Great presentation. You really helped explain networks to me in a better manner. And I had a question about the science DMZs. You mentioned how it was very different from a security aspect and that firewalls might not work. What are some security measures that work well in a DMZ environment?
Sure, yeah. So in a DMZ environment, often what we're using is what are called ACLs within the routers themselves, so that are able to actually protect and lock stuff out. So ACLs are a bit of an old school way of doing security. Basically, it's just dynamic lists of what can talk to what. But if you've got a very constricted environment where you know the point A's and the point B's, you can very effectively lock down an environment like that with ACLs. The routers are also able to process basically at line speed because these are very simple security measures. They're not doing deep packet inspections. They're not tearing apart the data or anything like that. So an access control list. Yep, sorry, I'm a network engineer by trade originally, so I tend to speak in acronyms. Thank you, Todd, for calling me out on that in the chat there. Yeah, access control list, absolutely. So those are often used around that. And there's different ways. Some people will actually have specialty firewalls that sit within the Science DMZ that can take care of that. There's firewalls that can be built out on servers, open source things that can work a little bit better and more effectively. The big thing there is to just make sure that there's that conversation between the security teams and the networking teams and the research teams, research support teams, to know that this traffic is different. So it's often very large, chunky amounts of data. It's very defined point A and point B. And you often have control of that data along the whole route. So it's not as risky of data. when it comes to that. So if you're bringing in a data set, it's not like you have a student or a staff member just going out and browsing the internet, randomly downloading stuff. This is very controlled data transfers. Often within science DMZs, the only devices that sit in there are the data transfer nodes, and you do everything through those, and those have security measures built into them as well, as far as who can access it, where you can get the data from, those sorts of things. It really does depend on having a good relationship with the information security team, making sure they understand what's going on and the problems that you're trying to solve, and looking kind of outside the box. Because a lot of information security folks are not necessarily come from the research side of things, don't necessarily understand the research side of things by default. So they need to understand that this is a different type of traffic than your normal internet browsing. Hopefully that answers the question.
Thank you very much. That definitely helps me and will be useful for some future conversations I'll have. Thank you.
Yeah, good. Don't avoid the conversation with your IT security folks. So they are no different than any other engineers or IT folks. They just need to understand what you're trying to do, understand what's going on. And as soon as they do that, you'll find that they become a lot more helpful often. Is Eduroam available for all academic users? I'm just going through some of the questions here online. Yes, as long as your institution has signed up for it and enabled it. If your institution hasn't, get in touch with your IT department, or get in touch with, if you're in the US, Internet 2, and they can go hopefully shame your institution into getting onto Eduroam. I think Eduroam is fairly wide deployment at this point in time. There's not going to be too many institutions that don't have it, but I'm sure there's still some out there. See, network, Jeff Woodward asks, what are some network monitoring tools that we ought to be proficient in? So I would say, talk to your network engineers, talk to your networking folks first, and see what they use as far as network monitoring tools, because they probably already have some stuff set up. One of the big ones that's used a lot in the research community is a package called PerfSonar, which basically allows you to deploy servers in certain areas that are able to do tests that are specifically designed around big data transfers in that. So if you run a supercomputing center, or if you run storage rates, stuff like that, talk to your networking folks who are involved in the research side of things, and ask them if maybe putting a PerfSonar server in right next to the storage or right next to the data transfer nodes or something like that would be useful, and have them help you with that, because that is very helpful when it comes to troubleshooting. It's the one package that I would call out, although there's tons of different ways to monitor and evaluate how traffic works. All right, friction-free networks, just a wish list or actual technology. So that's a marketing term. That's all that is. Yeah. So friction-free networks. I mean, that's what we say. Hey, we'd love to have friction-free networks, and that's what we're trying to build for. It's not an actual thing that you can just buy. It's more of an idea that we want our networks to be friction-free for the end users, for the researchers. So researchers have one thing in mind. They are trying to get whatever they're researching done. They're trying to get that task done. They're not trying to build necessarily technology. They don't necessarily even want to care about the technology. Often they have to care about the technology, but they don't want to necessarily care about the technology. If you're a genomicist who's sequencing large amounts of data sets, you don't want to have to worry too much about how you're getting data from point A to point B. That's not your thing. That's not what you're paid for. That's not what you went to university so many years for and got your PhD for. You want to be able to just simply move the data. And that's really our job as facilitators, as IT folks in universities, to make sure that we provide a friction-free environment for researchers. But it's kind of a marketing term for ourselves. It's not an actual thing that you can buy, if that makes sense. Any other questions folks have?
You answered. Oh, you did answer the one about the hardware measuring tools. Is that right?
So I sort of did when it comes to PerfSonar. yeah, so let me read that one in more detail here real quick. Yeah, so if you think back to my presentation there, if you're transferring something over a very small distance, which is what you're saying, that they're a computer with a Thunderbolt to 10 gig adapter, that's going to work fairly well. It's when you get outside of that, when you start to get that distance involved and more systems involved, is when problems start to happen. I would say that there are things like Persona and that there are a whole bunch of different tools that can be done for that. I would highly recommend that instead of asking me that you reach out to your local networking team and ask that question, because there may be things that are very applicable to your environment that wouldn't be necessarily applicable in a broader sense. I like to tell people that I used to be a network engineer. I like to still think that I am, but unfortunately, I volunteered for one too many things in my career and got promoted up to where I don't actually do work anymore. I just talk to people about work. So.
So I have one question, and it relates back to the friction-free networks. Why? Why do we want friction-free networks? And I'll provide a little context. I have been told, but I know approximately nothing about networking. I have been told that the problem is that research data flows look a lot like, for example, denial of service attacks to firewall appliances. Can you talk a little about that?
Yeah, absolutely. And that's actually a slide I should add to this presentation. So yeah, so one of the things that will stymie commercial networks or networks that are designed. So security folks are there to protect the network. They're there to protect what's going on. Denial of service attack is basically when often, there's many different types of it, but one type of denial of service attack is to just overwhelm your network with large amounts of data being sent. Doesn't even have to be validated, doesn't have to be anything, but just overwhelm all the equipment with so much data being sent that it kind of shuts everything down. So that often looks exactly like a researcher trying to move a whole bunch of data unexpectedly across the network. And denial of service attack boxes, again, they're built for that 98% of folks and of networks. Look at that, see it happening, say, whoop, shut that down. That doesn't look right. It doesn't look like normal internet traffic, and it isn't normal internet traffic. So it'll often get shut down there. We had a couple of instances here in New Zealand where it was very interesting, where did research flows over, university did a couple of research flows over a commercial network, and yeah, the stuff just got shut down immediately. And interestingly enough, the folks at the internet service provider who were the first internet service provider, the one that the university paid the money to, didn't know what was happening either, because what was actually happening, the denial of service was actually getting caught further upstream. It was getting caught by one of the providers and stopped. And it took many, many days to even get to figure out what was going on and why that was broken. And a lot of commercial service providers won't even spend that much time necessarily doing this. This is a unique situation where they were trying to prove some stuff around, hey, our network will work just as well as the research network. And they may have gotten their network to work just as well, but because they commercially just sell the traffic off, they didn't have any control over what the other commercial providers were necessarily doing. So that really did that there. Friction-free is really, really about making sure that our researchers want to use our networks, that do things in a proper way. So if we don't provide a way for the researchers to do this stuff that's easy and that's effective for them to do, they'll go figure out another way to do it. They'll put it on a giant hard drive and they'll ship it in the post, or they'll do something else that is even worse when it comes to data security. So really working with and building those connections is very important.
Hey, Wallace, what in your experience, what size, when's the threshold when you start seeing denial of service and actual issues with the research data that we're
it really depends. Yeah, it really depends. I mean, some of the smaller providers have fairly small thresholds on it because they're looking to protect, hey, if I'm a fairly small provider, I've got a 10 gig pipe to the internet. I want to make sure that doesn't get overwhelmed. So it really depends on the size of things in question. But it can be as small as a couple gigs to a couple hundred gigs where that starts to happen. It depends how the traffic is being flowed and how it's being done. because if you think about what most people do on their home internet connections or even on business internet connections, it's not transferring many gigabytes of files usually over long distances. It's often not about transferring. So if you're transferring a large amount of data, you're transferring, remember that train analogy I used earlier, it's a big long string of large amounts of information. That's not necessarily something that happens a lot on the regular commercial internet. Certainly not from endpoint to endpoint. So often, we're going from a very specific place in one institution to a very specific place in another institution. We're not going to a content delivery network. We're not going to one of the normal sources on the internet. So that looks very suspicious as far as most people are concerned. It's gonna really depend.
Thank you.
Yeah. I see another question on here. How have SDNs impacted infrastructure currently? And I'm assuming that you mean software-defined networks. So assuming that you mean software-defined networks, I mean, software-defined networking has basically, to me, it was been in networking while software-defined networks became this huge thing and then kind of died off, and just kind of now, it's just that normal technology curve that we all know about, as technology adoption curve. Software-defined networks are pretty much everywhere now out there. It is the way that companies are going. Being able to define how traffic flows in that is very important. You can do some really cool stuff with SDN on the back end. You can make networks that don't necessarily need separate hardware for research networks. Like we used to have to build research networks with completely independent hardware. Don't necessarily have to do that today. We can logically segment things and do stuff like that. The one thing I would caution on SDNs is that it does add quite a bit of degree of complexity into the situation. So you need to make sure that your staff, when it comes to the networking side of things, can handle that, are capable of it. I can remember being pitched by many business, many network vendor, hey, this is going to save you time, it's going to save you staff, all this kind of stuff. It doesn't. It makes it big improvements on things, but it doesn't necessarily do that. It's a big change there, and people need to learn how to operate it and run it. So TCP/IP protocol has a lot of overheads. Are the new protocols on the horizon? Absolutely. There's a whole bunch of them. There've been new ones pop up all the time. However, TCP/IP is the behemoth on the internet, on networks. It's not going anywhere anytime soon, and there's all sorts of issues with using newer protocols and that sort of thing. There are a bunch out there though, but I'm not the person necessarily to go into those and to talk about them in any sort of detail. Anybody else have any questions? Any that I've missed in the chat here?
So Wallace, I have a question. It's a great presentation, thanks. On one of your earlier slides, I think you were illustrating the effect of packet loss.
Mm-hmm.
And if I read the slide correct, it was a 10 gigabyte connection, but the y-axis on this seemed to max out at, I think it was 1 gigabyte. So is that kind of sort of what you should expect with those things because of like the TCP, handshakes and things like that, or?
Not necessarily. So that was a test that was done by ESNet many years ago, and it's a fairly old example at this point in time. You'd have to ask them exactly what the. In fact, I think they have a place on the ESNet website where you can go and explains in great amounts of detail that test and what they did and that. But yeah, I don't know any of the specifics around that. But you can certainly ask them, and they would love to chat about it.
Thanks.
Yeah, no problem. All right, anybody else before I turn it back over to Henry? Anybody have any other questions? Feel free absolutely to reach out to me at any point in time. Email, whatever. I'm always glad to talk or put people in touch with the people who actually know what they're talking about as opposed to me.
There are actually still a couple of questions. Do you want to answer them, or you've got about 5 more minutes?
Yeah, absolutely. Not a member of Eduroam. What is the value proposition in us joining? So Eduroam is great for one thing. So if you've got people visiting your campus from other institutions that use Eduroam, they can just immediately be on the Wi-Fi the moment they walk onto your campus. Doesn't require them to do anything special. Just they walk onto campus, their phone or their laptop or whatever just connects into Wi-Fi. They're on, they've got a connection. Same thing works for you when you go to another campus. So if you go to the thousands and thousands of the institutions across the US and the world that have Eduroam, the moment you're there, your device is connected to a network connection through the university or the research institutes. There are airports, there are all sorts of places around the world that have Eduroam. I'm amazed constantly the amount of times I'll walk down the street in a city or something like that and realize all of a sudden that I'm connected to Eduroam. Very handy. It's good there. I would say those are the value propositions there. Big clouds use TCP/IP or some proprietary protocols. Oh, I'm sure they've got both. I'm sure they've got proprietary protocols. They've got whole proprietary ways of doing networking within themselves. One of the tricky things that's happening right now within the networking community is that universities are stuck between being we have some needs of a very large cloud provider, but yet we're also more of the size of a mid-size to large business. And the networking equipment for a very large cloud provider and the networking equipment for a large enterprise has really diverged a lot in the last few years. So the features that are over on large cloud providers in hyperscale data center environments and that are very different than the feature sets that are on enterprise networks now. And then that's actually one of the things that is difficult for network engineers right now to deal with is kind of that difference between the two there and the divergence in the technology stacks. Yep, Eduroam for public libraries, absolutely. There's anybody can connect into that as long as you're reasonably associated with the community. I'd highly recommend you reach out to your local your state research network or directly to Internet 2 on their page. They'll have a place where you can link in and talk to about Eduroam there. Google has their own protocols. I'm sure they have their own protocol. I'm absolutely positive they do. Should university pay money to join Eduroam? I don't know the specifics of that question. I don't know why somebody's charging you money to join Eduroam. There may be a reason for it. I know in New Zealand, all I can talk about is in New Zealand right now, there's no cost to join Eduroam through RIANS. RIANS supports that, and there's no cost for that here. Maybe in your area, but that's more of a question I would say for who's ever charging you the cost. All right, any more questions?
Well, and we're at the end of our time. So let's give a virtual round of applause to Wallace for a fantastic session. Thank you very much. Let me stop the recording.
Thank you, everybody. And you're all invited to come visit me at the University of Otago in New Zealand. So
I think we'll all come as a group.
I won't put you up in my house, but I'll certainly give you a tour of campus.